Step inside a world where commercial aircraft are maintained and assembled with precision, while cutting-edge military planes are unveiled, showcasing engineering excellence and power. The startup of the F-22 Raptor reveals the power and sophistication of one of the world's most advanced fighter jets. As the engines come alive, a deep mechanical sound echoes across the runway, reflecting the aircraft's immense capability. The F-22 is a fifth-generation stealth fighter used by the U.S. Air Force to achieve air dominance. Its stealth design, internal weapons bays, and radar-absorbent materials make it extremely difficult to detect. During startup, the aircraft prepares systems that enable supercruise, thrust vectoring, and fully integrated avionics. These technologies allow the F-22 to fly at supersonic speeds, perform extreme maneuvers, and give the pilot unmatched situational awareness before the jet ever leaves the ground. The inspection focuses on verifying the correct operation of the aircraft's landing gear system. During the test, technicians command the landing gear to retract and extend while the aircraft is safely on the ground. Hydraulic systems, actuators, locks, and sensors are carefully monitored to ensure smooth movement and proper synchronization. The up and down check confirms that each landing gear leg locks securely in both positions. This procedure is essential for flight safety, helping prevent mechanical failures during takeoff and landing. A maintenance test verifies the A320 landing gear retraction system by cycling gear up and down, checking locks, hydraulics, sensors, and safe mechanical operation under supervision. The landing gear test of the Boeing 777-200 is carried out inside a maintenance hangar to verify the correct operation of the aircraft's gear system. During the test, hydraulic power is applied to extend and retract the nose and main landing gear while the aircraft is securely supported. Engineers closely monitor gear movement, door sequencing, locking mechanisms, and hydraulic pressure to ensure smooth and synchronized operation. Sensors and cockpit indicators are also checked to confirm accurate feedback to the flight crew. This controlled hangar test allows technicians to identify leaks, abnormal noises, or mechanical resistance without exposing the aircraft to external conditions. Successful completion of the test confirms that the landing gear system is reliable and ready for safe flight operations. Aircraft tires are engineered to handle extreme conditions. Despite being only about 45 inches of rubber, they support hundreds of thousands of pounds and absorb landings at speeds over 170 miles per hour. Made from reinforced synthetic rubber and inflated with nitrogen, they resist heat, pressure changes, and heavy impacts reliably. During hangar maintenance, an emergency slide deployment test was carried out on the upper deck escape slide of this Boeing 747-400 ERF cargo aircraft. In an emergency, crew can evacuate using this slide, overhead hatch escape reels, and the rope escape system at door 5L installed on board. The ultimate load wing test of the Airbus A350 XWB is a critical structural certification process designed to verify the strength and safety of the aircraft's wings. During the test, Hydraulic actuators gradually apply increasing upward forces to the wings, simulating extreme aerodynamic loads far beyond those experienced in normal flight. As the load rises, the wings bend dramatically, demonstrating their flexibility and composite material performance. The test continues until the wing reaches its ultimate load limit, confirming that the structure can withstand maximum stress without catastrophic failure, ensuring safety, durability, and compliance with aviation regulations. The replacement of fan blades on a Boeing 777 is a critical maintenance procedure carried out to ensure engine safety, efficiency, and reliability. The process begins with securing the aircraft and shutting down the engine, followed by the removal of the engine inlet cowling to provide clear access to the fan section. Technicians carefully inspect the fan blades to identify damage such as cracks, foreign object impact marks, or excessive wear. Once the faulty fan blade is identified, it is precisely indexed and removed using specialized lifting and locking tools to prevent stress on the fan disc. Each blade is individually designed and balanced, so the replacement blade must match the exact specifications and weight requirements. The new fan blade is then installed into the fan disc slot and securely locked in place. After installation, technicians perform alignment and balance checks to ensure smooth rotation and prevent vibration during operation. The engine cowling is reinstalled, and a detailed inspection is completed. Finally, the engine undergoes functional tests to confirm that the fan assembly operates correctly, maintaining the Boeing 777's high standards of performance and flight safety. The assembly process of the Saudi Boeing 787-9 Dreamliner HZ era begins when the major aircraft sections are transported to Boeing's final assembly facility. Large structural components such as the forward, center, and aft fuselage sections, along with the wings and tail assemblies, arrive fully manufactured and pre-equipped from global partner plants. These oversized sections are carefully unloaded and moved into the final assembly line using specialized transport systems designed for precise handling. Inside the assembly hall, the fuselage sections are positioned using laser-guided alignment tools to ensure exact dimensional accuracy. Technicians then join the sections together using advanced fastening and bonding techniques, creating a single, continuous fuselage structure. Structural frames, floor beams, and pressure-resistant joints are secured to maintain strength and pressurization integrity. Once the fuselage is fully joined, the wings are attached to the center wing box. This step requires extreme precision, as the wings support fuel storage, flight control systems, and aerodynamic loads during operation. After wing installation, the horizontal and vertical stabilizers are mounted to the rear fuselage, completing the aircraft's primary structural configuration. With the airframe assembled, system installation begins. Electrical wiring, hydraulic lines, and flight control actuators are routed throughout the aircraft. The Boeing 787-9 relies heavily on electrically powered systems, so extensive integration work is performed to connect power distribution networks and ensure system redundancy. Avionics components, sensors, and flight control computers are installed and connected at this stage. Next, the engines are mounted beneath the wings using reinforced pylons. These engines are carefully aligned and connected to fuel, electrical, and control systems. After engine installation, landing gear assemblies are fitted, allowing the aircraft to support its own weight. The final stages include interior installation, system calibration, and functional testing. Ground tests and flight trials are conducted to verify performance, safety, and reliability before the aircraft is approved for delivery. Upon completion, the fully assembled Boeing 787-9 Dreamliner HZARA is prepared to enter service with Saudia. From testing philosophy to production, the Boeing 747-8 program demonstrates how safety validation, engineering discipline, and large-scale industrial coordination define the creation of one of the most complex machines ever built. Before full production is allowed to continue, the aircraft must survive a series of extreme tests designed to push every system beyond normal operational limits. One of the most demanding procedures is the rejected takeoff test. During this test, the 747-8 accelerates down the runway at near takeoff speed before the pilots apply maximum braking force. The brakes absorb enormous energy, causing them to glow red from heat. Fire crews are positioned nearby, not to intervene, but to observe and verify that temperatures remain within acceptable limits. If fire or structural failure were to occur, the aircraft would immediately fail certification. This test proves that the aircraft can abort a takeoff safely and still allow passengers to evacuate. Boeing expects this to be the only rejected takeoff the aircraft will ever experience, but demonstrating this capability is mandatory. Only after passing such tests can the aircraft proceed confidently through the remaining stages of production and assembly. The 747-8 is the most modern evolution of the jumbo jet. It is the longest commercial aircraft ever built and the most efficient in its category. Like all previous 747 models, it is manufactured in Everett, Washington, inside Boeing's enormous assembly plant north of Seattle. This megafactory is the largest building in the world by volume. Its doors form the largest mural ever recorded, and the interior space is so vast that clouds have occasionally been observed forming near the ceiling, 11 stories above the factory floor. Inside this vast structure, the factory operates like a self-contained city. It has its own fire department, internal transportation system, and several of the busiest cafeterias in the region. Workers use bicycles and tricycles to move between work zones, and even experienced employees can take months to learn the layout. Despite the apparent chaos of aircraft parts scattered across the floor, every operation follows a carefully planned sequence. Each aircraft occupies a dedicated assembly position, and every task is performed according to a strict schedule. For nearly 4 decades, the Boeing 747 was the undisputed king of the skies. That reign ended when the Airbus A380 surpassed it in size and passenger capacity. With 2 full passenger decks and seating for more than 550 people, the A380 addressed the rapid growth in global air travel. However, airlines were no longer looking only for size. Rising fuel prices and environmental concerns made efficiency the most critical requirement. The older 747 became expensive to operate and less competitive. Rather than abandoning its flagship aircraft, Boeing chose to reinvent it. Designing a completely new airplane would have required more than a decade and billions of dollars. Instead, Boeing decided to radically redesign the existing 747 platform, transforming it into a more efficient and environmentally responsible aircraft. The result was the 747-8, capable of flying faster, traveling up to 1/3 of the way around the world without refueling, and burning less fuel per seat than any previous 747. Although the Airbus A380 remains larger, the 747-8 consumes less fuel per passenger, an important factor for airlines making long-term fleet decisions. To achieve these improvements, Boeing relied on technologies already proven on the 787 Dreamliner, including advanced aerodynamics, modern engines, and digital flight control systems. The Everett facility functions primarily as a final assembly center. Components arrive from every corner of the world. Passenger seats come from Germany, wing structures from China, and flaps from Australia. A single 747-8 requires more than 6 million individual parts, and every one of them must arrive at exactly the right time. Boeing uses a just-in-time production system to minimize inventory costs. Parts are delivered only when they are needed, reducing storage requirements and capital investment. However, this system leaves little margin for error. Any disruption can delay the entire production line. To prevent interruptions, Boeing ensures that critical components never run out. The most valuable of these are the engines. Each engine costs approximately $20 million, making it impractical to store them for long periods. Engines are installed only 1 or 2 days before the aircraft leaves the factory, arriving precisely on schedule. Every component, from massive structural sections to small tools and fasteners, is electronically tracked. A single missing bolt could cause a disaster if it entered an engine or fuel tank, so quality control is uncompromising. Production begins with the wings, the most important aerodynamic components of the aircraft. The wing assembly area occupies nearly a quarter of the space dedicated to the 747 program. The wings of the 747-8 are the largest Boeing has ever built. Each wing is large enough to support 4 average-sized houses on its surface. Internally, each wing consists of 3 main spars running along its length, connected by 55 ribs. This structure provides the strength needed to support the aircraft's full weight during flight, turbulence, and landing. Each wing must also safely carry up to 58 tons of fuel. Aluminum skin panels are attached to the structure using thousands of rivets. Every rivet is critical. Workers install each one carefully and then return to inspect them again. Errors at this stage could cost lives, so every fastener is treated as a safety-critical item. As the wing takes shape, its aerodynamic profile becomes clear. Earlier versions of the 747 used wing designs based on 1960s technology. The 747-8 adopts advanced aerodynamic concepts derived from the 787 Dreamliner, increasing lift while reducing drag. During flight, air flowing over the wing creates low pressure above and higher pressure below, generating lift. At the wingtips, however, air from the lower surface curls upward, forming vortices that increase drag. To reduce this effect, the 747-8 features raked wingtips angled upward. These wingtips push vortices farther from the wing's surface, reducing resistance and improving fuel efficiency. However, flight tests revealed a new challenge. Engineers detected a small vibration in the wings known as flutter. In certain conditions, the wings oscillated by up to 5 centimeters. In extreme cases, uncontrolled flutter could cause structural failure. Rather than redesigning the wing, engineers applied a modern solution. The aircraft's fly-by-wire system uses computers to interpret pilot inputs and control flight surfaces electronically. Sensors detect vibrations, and the computer makes small, rapid adjustments to counteract oscillations. This system actively damps flutter during flight, maintaining stability even at the edges of the flight envelope. While the wings are assembled, work continues on the fuselage. The fuselage is built in multiple large sections, including the nose, the central section with the distinctive hump, and the rear section. Each section is assembled panel by panel and covered with green protective vinyl to prevent damage. The lower fuselage is built upside down to allow easier access. Once complete, it is rotated 180 degrees using specialized equipment. A single fuselage section is so heavy that it requires a crane capable of lifting 34 tons. 26 cranes operate on more than 50 kilometers of tracks throughout the factory, transporting sections between stations. Before any section is moved into its final position, workers carefully inspect it to ensure that no tools or loose parts remain inside. Joining the fuselage sections and wings is one of the most complex operations in the entire process. This stage is usually performed at night, when fewer people are present and the risk of error is reduced. Alignment tolerances are measured in millimeters. First, the forward fuselage section is positioned to receive the wings. The wings occupy nearly the entire width of the factory floor, leaving only a few centimeters of clearance between the wing tips and the walls. Two tractors pull the wings at exactly the same speed to prevent lateral movement. Once the wings are secured, the rear fuselage section is attached. As the sections come together, the unmistakable silhouette of the jumbo jet finally emerges. The completed airframe measures 76 meters in length and 68 meters in wingspan. Thousands of workers contribute to this moment, coordinating their efforts with precision developed over decades. After structural assembly, attention turns to the engines. The 747-8 uses 4 advanced General Electric engines, the most efficient ever built for this aircraft. Earlier 747 engines consumed more than 12,000 liters of fuel per hour. The new engines burn significantly less while producing greater thrust. Composite materials reduce engine weight by 180 kilograms each, allowing increased payload or passenger capacity. The engines are also the quietest ever installed on a 747. Installing each engine is a delicate operation. Concrete blocks are placed inside the fuselage to prevent the aircraft from tipping backward. Each engine weighs 7 tons and must be aligned precisely. Only 8 bolts secure each engine, tightened to exact torque values. The front mounts are designed to break away safely in the event of a severe failure, allowing the engine to separate without damaging the wing. With engines installed, technicians begin testing the aircraft's electrical systems. The 747-8 contains enough wiring to supply power to more than 50 houses, with kilometers of cables running throughout the airframe. All systems converge in the electronic bay, which functions as the aircraft's nervous system. The fly-by-wire system is not fully automated. Pilots command the aircraft, and computers interpret those commands. Multiple layers of redundancy ensure that if one system fails, others can take over. Interior completion follows. The 747-8 interior draws inspiration from the Dreamliner, featuring improved lighting, modern colors, and increased comfort. Each airline customizes the interior according to its own branding. Before painting, the protective vinyl is removed. A base coat is applied by hand, followed by multiple layers of paint. Weight is carefully controlled, as excess paint increases fuel consumption. A typical paint job uses about 500 kilograms of paint. Before delivery, the aircraft undergoes extensive flight testing. Test pilots push the aircraft beyond normal limits, performing extreme maneuvers. Load distribution tests use water ballast pumped through barrels to simulate different cargo and passenger configurations. Minimum takeoff speed tests deliberately scrape the tail on the runway using a protective block to ensure safe rotation. The airshow presents a breathtaking demonstration of precision, discipline, and aerial skill by the U.S. Air Force Thunderbirds. The fighter aircraft they use for this performance is the F-16 Fighting Falcon, a highly maneuverable multi-role jet known for its speed, agility, and reliability. The show begins with the roar of F-16 engines as the aircraft take off in tight formation, immediately capturing the attention of the audience. Flying only a few meters apart, the pilots demonstrate extraordinary control as they climb steeply into the sky. The Thunderbirds then perform synchronized rolls, high-speed passes, and dramatic vertical maneuvers that highlight the aerodynamic capabilities of the F-16 Fighting Falcon. One of the most impressive moments of the display is the opposing solo maneuvers, where two aircraft fly toward each other at high speed before crossing with perfect timing. These passes showcase not only the performance of the aircraft but also the pilots, intense training and trust in one another. Throughout the show, formations such as the Diamond and Delta are maintained with remarkable accuracy, even during sharp turns and rapid altitude changes. The F-16's powerful engine allows for sudden acceleration and near-vertical climbs, while its responsive flight controls enable smooth transitions between complex maneuvers. Smoke trails are used to enhance visibility, helping spectators follow each movement and better appreciate the precision of the choreography. Overall, the Thunderbirds' aerial performance is more than just entertainment. It is a powerful demonstration of teamwork, professionalism, and the advanced capabilities of the F-16 Fighting Falcon, leaving the audience inspired and impressed by modern military aviation. During the Marine Festa in Hachinohe 2013, one of the most striking demonstrations was the infrared decoy launch conducted by the missile boat JS Kumataka of the Japan Maritime Self-Defense Force. This exercise was designed to show the public how modern naval vessels protect themselves against heat-seeking threats in real combat situations. As the JS Kumataka maneuvered offshore, it simulated a defensive response to an incoming infrared-guided missile. At the command point, the crew activated the ship's countermeasure system, releasing bright infrared decoys into the air. These decoys burned intensely, creating strong heat signatures intended to divert enemy missiles away from the ship. The launch was clearly visible from the observation area, with multiple flares spreading outward and slowly descending over the sea surface. The demonstration highlighted the importance of electronic and infrared countermeasures in modern naval warfare, where survival often depends on rapid detection and immediate response. Through this realistic display, spectators gained a rare insight into the defensive technologies and high level of training required by JMSDF crews. The JS Kumataka's decoy launch effectively illustrated how missile boats operate under threat while safeguarding both the vessel and its personnel. At Osan Air Base in the Republic of Korea, U.S. Air Force weapons technicians from the 25th Fighter Squadron carry out the installation of the iconic GAU-8/A Avenger Gatling gun on an A-10 Thunderbolt II aircraft. On August 29, 2023, the maintenance team carefully prepares the aircraft and the weapon system inside a secure hangar environment, following strict technical and safety procedures. The GAU-A Avenger, a defining feature of the A-10, is methodically positioned and integrated into the aircraft's nose section. Technicians work in coordinated steps using specialized ground support equipment to align the gun accurately with the airframe. Each mounting point, connection, and interface is inspected to ensure the system fits precisely and meets operational standards. Throughout the installation, squadron personnel conduct detailed checks on mechanical components and related systems. Their focus is to verify that every part functions correctly and reliably, from structural attachments to system interfaces. This careful attention helps guarantee the aircraft's readiness for future missions. The work performed by the 25th Fighter Squadron supports the operational capability of the A-10 fleet and contributes to maintaining regional security. By ensuring the aircraft and its weapon systems are fully mission-ready, these technicians play a vital role in sustaining U.S. Indo-Pacific Command operations and reinforcing stability across the area of responsibility. The demolition of a retired Boeing 747 begins with careful positioning of two heavy excavators equipped with powerful hydraulic grapple buckets. Once the aircraft is secured on the ground, the excavators move in from opposite sides of the fuselage to ensure stability and control during dismantling. One machine grips the aircraft's outer skin, while the other applies force to tear through the aluminum structure, separating large sections in a controlled manner. The process starts at the upper fuselage and wings, where the grapple buckets clamp down and peel away panels like sheets of metal. As the structure opens, internal systems, such as wiring, insulation, and tubing, are exposed and removed. The excavators work in coordination, alternating between pulling, crushing, and cutting motions to prevent uncontrolled collapse. Next, the wings and tail section are broken down into manageable pieces. The hydraulic clamps easily shear through spars and ribs, demonstrating the immense strength of modern demolition equipment. Larger components are set aside for further processing, while smaller debris is collected and cleared from the site. Throughout the operation, safety and efficiency remain priorities. The systematic breakdown of the Boeing 747 allows valuable materials to be recovered and recycled. What was once a massive long-haul aircraft is gradually reduced to raw materials, completing the final stage of its operational life through industrial recycling.